Moment.
That is Professor Amartya Mukhopadhyay from the department has been awarded with the Research Dissemination Award of the Institute. Professor Amartya Mukhopadhyay did his doctoral in materials research at University of Oxford, UK in 2009 and completed his postdoctoral research at Brown University, USA. Include materials for electrochemical energy storage, which is a very important topic of the day. Particularly, government has already announced by 2030 we will have only electric vehicles. So from that point of view, this is a very important research area. During his research over the years, Professor Mukhopadhyay has been awarded with the INAE, that is the Indian National for Engineers, Young Engineer Award in 2016, ASM IIM North America Visiting Lectureship in 2016, where he visited a couple of universities in North America. Then he also received the IIT Bombay Young Investigator Award in 2014, Dr. R.L. Thakur Memorial Award as Young Scientist by the Indian Ceramic Society in 2013. He's also been recognized as the emerging investigator by the Royal Society of Chemistry, UK. Presently, as I said, he is actively working in lithium and sodium-based batteries. Lithium has its own problem, though the lithium batteries are the best as of now, but lithium is limited in the core, and therefore we are looking at sodium, and that is the latest that he's been working on. Let us hear Professor Amartya Mukhopadhyay what he has to say about his latest research in batteries.
Thanks, Professor Dusane, and thanks to IRCC for providing me with this opportunity to present something in front of a wider audience. So, from the previous talk, we heard that Aswani is converting sunlight to electricity with a very good efficiency. Not only that, she is also converting moisture to electricity. And Professor Dusane has been converting solar energy to electrical energy with silicon-based solar cells since ages. So I think there should be some people who should be able to store that. So forget about people. I think these are the alkali metal ion batteries, which are the systems which are supposed to store energy harvested from renewables. That's of course one of the things which they can do. They can be used for many other applications, like we know we have these cell phones and laptops with lithium ion batteries. So today I thought that since it will be a wider audience and I was expecting like a lot of students as I already have. So let me go to some of the very basic concepts and give some brief introduction to some of the concepts on which the performance of these alkali metal ion batteries depend, more from a materials perspective, which in fact influence the electrochemistry of the same. Towards the second half of the talk, I will discuss a little bit about the stress development and maybe show glimpses of some of the things which my students have done. But overall, I am not going to focus on any particular research or any particular research project or research aspect in today's talk. So before going into the details, let me just give you a glimpse of what we do in our group. So we work on two verticals. One is electrochemical energy storage, which is what the alkali metal ion batteries are. And for that, we look into the electrode materials, the effect of their structure, composition on the electrochemical behavior. And so not only the electrode materials, we also look into the solid state lithium ion batteries or the solid electrolytes, and ultimately try to make cells which do perform quite well. Other than that, we work on structural ceramics, and where like one of the things we have done is develop ceramic alloys, going away from the typical ceramic composites. And Lav Gurnani, one of my students who should be graduating soon, has done excellent work with the ceramic alloys. And we also do some work with the carbon nanotube reinforced ceramic materials. So looking into the research on battery materials, so we work on various types of materials and looking at the materials perspective, like the structure, morphology, etc. and with special focus of late is of being on the transition metal oxides for lithium ion battery as well as sodium ion batteries. And like for some of the materials which show very poor cyclic stability because they undergo huge dimensional changes during the lithium or sodium insertion removal, we try to understand ways in which that can be suppressed, and one of the ways is usage of buffer interlayers, and we have tried to understand how they can help so that one can make really good stable electrodes. And as I mentioned, like we also working on solid electrolyte with Amartya, and so the ultimate goal is to develop solid state lithium ion cells, which are as of now like in its infancy, I would, if I say, because nobody knows how to make a good lithium ion cell with a solid electrolyte. There is no established methodology of making a cell having a solid electrolyte, unlike like fabrication of cells with a liquid electrolyte. I borrowed this slide from my recently graduated PhD student Manoj Jangit, so who will be joining University College London in a few months' time as a postdoctoral researcher. So this shows the sequence of events towards the development of the lithium-ion batteries which we know today. So it all started with Lewis doing some experiments with lithium as one of the electrodes and trying to tame it to make batteries out of it. But then the first notable breakthrough was achieved when Stanley Whiting have developed a material which was TiS2, which could intercalate lithium in its lattice. So here we are talking of storing lithium in the lattice structure, in the lattice sites, and not really in the pores, which is very different from storages of say carbon dioxide, as we heard earlier in the day today, or maybe storage of charges in a capacitor. So it's very different because lithium will go into the lattice and sit in the lattice sites of the material. Following this, there was some work in trying to use lithium to develop different cells. And another breakthrough came when Goodenough with co-workers developed lithium cobalt oxide, which became the first stable cathode material for the lithium-ion batteries and leading to a cell voltage of more than 3 volt. Titanium disulfide was not a very stable material, and it was like it would lead to a cell voltage of about 2 volt, which is nothing much different from the nickel metal hydride that we used to have and we still have. So then, like the moment lithium cobalt oxide was developed, it became a major breakthrough in the area of lithium-ion batteries. However, one issue was still not solved, and that was there was still lithium on the other side acting as the anode, and which is good, will lead to very, very high energy density for the cell. However, it can lead to plating followed by dendrite formation of lithium, which can penetrate the separator and hit the cathode, leading to short circuit, which would lead to voltage drop and can also cause fire hazards. So lithium from the anode side had to be replaced, and that is where Rachi Diazami, a Moroccan researcher, came into the picture, and he developed the anode material which could again intercalate the lithium in its lattice structure, and he came up with the graphite intercalation, or electrochemically intercalating lithium in the graphite and doing it reversibly. So then this led to the development of the, I would say, the almost the present generation lithium ion cells having graphite as the anode and lithium cobalt oxide as the cathode. After that, from like Sony introduced commercial lithium ion cell based on a very, very similar concept, and like Ashai Kashai company was the first one to develop a prototype of the working lithium ion cell, again based on the concept of Goodenough's work and Rachi Diazami's work. And after that, there were like with the commercial lithium ion cell being developed and being like starting to get used, people worked on a lot of areas trying to improve the energy density and the stability of the lithium ion cells. And as we all know, in 2000, the Nobel Prize was awarded, like not 2000, but this year or last year itself, the Nobel Prize was awarded for lithium, for the development of lithium ion battery. And it went to the 3 scientists who were pioneer in that. So it went to John Goodenough, Stanley Whittingham, and I'm forgetting the name, but the Akira Oshiono from Ashai Kashai company. So, but the person who missed out was Rashid Yazami, which was a sad episode, but things go that way. Anyway, so the Nobel Prize in 2019 came because lithium-ion batteries could be like taken forward from being used just for portable electronic devices to much larger scale applications like electric vehicles and grid energy storage. And that was possible because primarily because the capacity of the cathode material could be further improved from going from lithium cobalt oxide developed by Goodenough to a very similar cathode material, but replacing a little bit of cobalt with other transition metals. But still, the anode material remained the same. It was graphite at this time, and it is still graphite in the present lithium-ion cells. Maybe a few lithium-ion cells as of now have a little bit of silicon along with graphite, but it is primarily graphite. Though the cathode, there are a lot of varieties of the cathode materials which are used in the commercial lithium-ion cells. So, like for the different applications, one would need different energy densities or different capacities of the lithium-ion cells, and they can vary from say watt-hour to the megawatt-hour level. Like what we use in the laptops and cell phones, they will typically have a capacity of around or energy of about of the order of watt-hour, whereas those used in the grids they will have around megawatt-hour. However, the energy that is stored, as you can see from here, the big range, it all comes when like individual cells which are the same lithium ion cell, it may be the same lithium ion cell as used in here and used in here. However, when it is packed together in like connected together in series and parallel, one can increase the voltage and the capacity to lead to a higher and higher energy containing device as is needed for the application. Nevertheless, the heart of the lithium ion battery pack still remains in the cell, and the performance of a cell are governed by the materials and electrochemical aspects. If one talks about materials, these are the materials which are very, very important. The basic functioning depends on the electrode. The electrolytes are very important for transportation of the lithium ion or the sodium ion in the case of a sodium ion cell between the two electrodes, and the current collectors which are connected to the external circuit. And of course, the interfaces can create a lot of problems, and that is why they are also important to or very important to look into. So this is how the basic working principle of sodium ion of a lithium ion or a sodium ion battery looks like. So during charging, the lithium ion would shuttle from the cathode, that is a lithium cobalt oxide, to the anode, that is a graphite. So any cell that is assembled is in a discharge state because the entire lithium is contained in the cathode or the lithium cobalt oxide or its variants. And then during charging, it will go to the graphitic carbon, get stored in its lattice, and again when one is like using it for some application, the lithium ion will shuttle back through the electrolyte from the graphitic carbon to back to the lithium cobalt oxide, and one will get electrons in the external circuit to balance that. So now this looks very simple, but then as I mentioned, the characteristic of the material and the interface between the electrode material and the electrolyte play a big role in determining the performance and the properties of the cell. As one can see, it's very interesting here. So graphite does not have lithium in it. So lithium is intercalated into the graphitic structure, and one may also consider that it is a kind of like transition metal oxide where lithium is intercalated. So overall, it is like at the interface, it's the same electrochemical reaction, that is lithium plus going to lithium, one electron reaction. However, there is a huge range of voltage that can be generated by using different materials, and that is an interesting aspect. So it all happens because the ultimate voltage that we see is not just a function of the like voltage associated or the potential associated with the one electron transfer reaction, but the entire thermodynamics of how it gets stored in the material and in what sites does the lithium ion and the electrons get stored. So that determines the entire range of cell voltage. Now, talking about that, if one looks into the very, very basic thermodynamic principles and consider one elementary reaction like a host in which the lithium ion, which is the A plus here, will get inserted and forming the lithiated host. If one looks into this very simple reaction, then the equilibrium potential associated with this reaction will be given as per Nernst equation by the change in free energy, which can be approximated in terms of the change in internal energy, because P delta V term becomes becomes negligible compared to the change in internal energy. So overall, it is this change in internal energy which governs the equilibrium potential. So in other words, if the lithiated host is more stable compared to the unlithiated host, then of course this E goes down, and so the difference between these two go up, and accordingly one gets a greater equilibrium potential. So in terms of thermodynamics, that is what it is, and that is exactly what governs the equilibrium voltage of lithium storage or sodium storage or potassium storage in any material electrochemically. So this is the inference, like if the difference is greater, or if the lithiated or sodiated material is more stable as compared to the unsodiated, unlithiated host, then it will lead to a greater voltage. But all of these depend on where the electron that is coming in from the external circuit and the lithium ion that is coming into the structure is getting stored. For example, if the lithium ion is getting stored in the octahedral site, it will lead to one equilibrium voltage. If it is getting stored in another type of site, say prismatic, lithium does not get stored in a prismatic, sodium gets stored in a prismatic, but suppose tetrahedral, it will lead to another cell voltage, even if the electron is coming to the same energy level. And then if the lithium is going into just one type of site and the electron changes the energy level to which it goes, that will also change the equilibrium voltage, because it will change the overall energy of the reaction. So, and like if one looks at it a bit more carefully, those materials which form a weaker bond with lithium, like for instance in graphite, lithium will stay in the van der Waals space between the graphene layers. When it's a metallic material, lithium will form a metallic bond with the host material. But when one looks at these, which are used as the cathode material, giving a high equilibrium voltage, in these lithium will form an ionic bond, which is a much stronger bond and leading to a much greater voltage. So the voltage is not just sufficient for high energy density, one also needs capacity, which is basically the amount of lithium that can be stored, or like equivalently the amount of electron that can be stored per unit mass of the material. And that is so this entire map shows a variety of materials with different capacity and different voltage with respect to some reference. In this case, it is the lithium plating on lithium which is used as the reference, which that is taken as a 0 volt. However, there is another aspect which is important, is like how stable are these materials upon repeated lithiation, delithiation. That is the cycle life of this material. Anyway, looking at the fundamental aspects of the voltage profile, so one looks at these are all the cathode materials where lithium will form a predominantly ionic bond with the oxygen lattice. However, one sees not only are the voltage different between different materials, but even if something starts at the same voltage, the voltage profile is very different. Sometimes it is very flat, sometimes it is slopey. Now, it is very flat when the oxygen network is quite robust, so that during further lithiation, delithiation, the energy of the site where the lithium is going into does not change appreciably. So then the overall energy will remain the same irrespective of whether you put 0.5 lithium or whether you put 1 lithium, and so the voltage remains like absolutely flat. However, if there is some deformation taking place in the oxygen lattice, then the site energy will change, even for a similar site like octahedral site, and so the voltage will become much slopey. So it is again just the materials aspect, a solid state chemistry aspect, which is governing the electrochemical behavior in this case. Now, I talked about the site in which the lithium is going in. As one can see, same material, it is LiMn2O4, like coming from Mn2O4 to LiMn2O4 to Li to Mn2O4. The transition metal redox, which is like leading to the charge compensation when the lithium is coming in, is Mn3 plus 4 plus. In other words, all the electron which are coming from here to here are going into the Eg band of the manganese 3d oxygen 2p orbital. So that remains the same. However, here lithium ion is going into the tetrahedral side, the smaller side, and here the lithium ion is going into the slightly bigger octahedral side, and that makes a difference in the energy and accordingly the voltage, which one sees as the voltage output. And that is simply because one needs to spend more energy to extract a lithium from the smaller tetrahedral side as compared to in an octahedral side. So it's the energy difference which leads to a huge jump in the voltage. Some of the things which the electrode materials undergo during the progress of lithiation delithiation, it is anyway a foreign ion going into a host lattice. So there will be transformation, and there, like in most materials, there will be lot of phase transformations, as we say, like first order phase transformations. Like one sees it goes from, like lithium cobalt oxide, the workhorse cathode goes from hexagonal to monoclinic phase during the progress of lithiation, and that will lead to jump in the lattice parameter, which is not good for the material because it can lead to lot of defect substructures and also cracking. Slowly I'm moving into the stress aspect. Again, very similar material, lithium transition metal oxide, something which is used nowadays in most lithium-ion batteries. So that also undergoes phase transformation from the layered structure to the spinel to rock salt structure, starting from the surface of the material. And if these non-layered structures form, they create a lot of hindrance towards the insertion, deinsertion of the lithium ion. So which is bad for the stability of the electrode over multiple lithiation, delithiation cycles. This is another example from tin, from our work itself, and so which shows that like tin is a classic example where like it keeps forming different tin lithium intermetallic phases during the progress of lithiation. If one looks at the potential profile, for different phases there will be different potential at which the lithiation is taking place, and the flat region corresponds to the phase transformation region where both the phases are in equilibrium. So there are various ways in which the stress development takes place in an electrode. Now, if there is a phase transformation, there will be mismatch between the two different phases, and there will be lot of stress at the mismatch between the two phases because they have different lattice parameters, different dimensions, and so that can be classified as an internal stress. However, like there are a lot of materials which expand and contract quite appreciably during lithiation, delithiation, and they will face constraint from current collector which are inactive and constraint from particles surrounding each other when they will impinge on them. So these are the various, like in brief, these are the mechanisms by which lead to the stress development in the electrode materials. So what does stress development do? It leads to cracking and disintegration of the electrode. Not just, there is a passivation layer which forms on the top of the electrode material, and it also can get cracked due to the stress development. It affects the thermodynamics and it increases the voltage hysteresis, which negatively affects the efficiency with which the energy can be stored and released. So it is extremely important to monitor the stress development in the electrode materials, if possible in real time during the electrochemical cycling, and that is one of the things we do. So like this is what you see here, it's a voltage plot, or it's a stress plot from the measurement, and like with the help of my collaborator from mechanical engineering, Tanmay, so we could get it modeled and develop understanding of the degradation of tin based electrode during the electrochemical lithiation, delithiation, and we saw it is primarily during the phase transformation regimes where the cracking and plastic deformation cum cracking of the electrode starts taking place. Not just tin, but it's the same thing for lithium cobalt oxide, something which people had not looked into in detail, even though lithium cobalt oxide has been in use since 1991. So we saw that again during the phase transformation regime, which corresponds to the plateau, there is a stress instability and stress drop, signifying that there is fracture that is taking place during this stress plateau. coming to constraining effect, so we can see this is silicon electrode getting lithiated. Silicon is one of the electrode materials which people are trying the level best to have it used in lithium ion cells, but still now not much lithium ion cells use silicon based electrode, primarily for this reason, because they undergo expansion by up to 300 volume%, and accordingly they face lot of constraints. And this is how a silicon electrode appears after, like, I mean, cycling for say 40 cycles, like 40 times lithiation delithiation from Manoj's work. So it looks like the top view shows that it's totally separated, disintegrated, and cross section view gives some funny morphology. So, like, in order to stop this, some buffer interlayers can be used, where we so in this case it's a multi-layered graphene, again coming from Manoj's work, and compared to this without any interlayer, one can see that after same number of cycles the electrode retains much better integrity. In fact, from this work we gained a lot of insight why graphene as a buffer layer helps, and we figured out that it's more to do with the interface between silicon graphene and interface between silicon and the current collector. So one can see excellent cyclic stability in the presence of graphene as compared to without graphene. So moving forward, we tried to see, instead of graphene, if one can use some material which can undergo pseudo-elastic deformation and accommodate lot of strain reversibly upon, like, extension and release. So this is a well-known material, NITI-based shape memory alloy, which are used for various applications, and we saw that it is also good for this application. And of course, like, we tried to understand why it is so. Another aspect which I have not mentioned so far, which causes stress development, is formation of passivation layer on the top. So when a bare electrode is exposed to the electrolyte, and during the initial stages of cycling, a passivation layer forms on the top of the electrode. And so this passivation layer is known as solid electrolyte interface, and when it forms, it kind of protects the electrode from further reaction with the electrolyte. However, it also leads to lot of irreversible capacity loss, primarily in the first few cycles, and as we found out, it also leads to a development of huge compressive stress which does not get reverted back. And then, like, looking into it more closely, we realize that formation of this passivation layer is nothing but an electrochemical deposition of some film on the electrode material, which is now acting on a substrate, and these are known to lead to development of stresses both in the film and in the substrate. So this is nothing different from that. So with this, let me thank the funding agencies, starting with IRCC, of course, and my collaborators, of whom Professor Dusane is one of them, and then RRCAT for allowing us to use the synchrotron facility, and of course the students and the postdoctoral researchers, so who have done most of the, all the work that I've shown here today, some of which I've shown here today. So they have been doing a lot of work, and with this, let me leave you at the summary slide, which you can go through and ask me whatever question you would like to, and I hope I may be able to answer some of them.